Before I start this video, let me take 30 seconds to tell you something about Exergic. Exergic is India's most trusted and most experienced institute for online GATE preparation. I am Chandresh Mahajan, founder and chief educator at Exergic. I am an All India rank 37 in GATE Mechanical Engineering, an ex-Indian Oil officer having 7+ years of teaching experience as of now. These are the GATE 2021 Mechanical Engineering toppers from Exergic. You can find their preparation strategy on Exergic's website. To know more about our GATE courses, you can visit our website or contact us on these details. Also, you can download Exergic GATE preparation app from Google Play Store. The link is available in the description of video. Now let us solve another problem here, and the problem that we are going to solve here, it is going to be again a conceptual one. You will learn something from this question for sure, and this question and the concepts of this question can definitely be asked in GATE either as the full question or a sub part of this question. Have a look at the question. It says that two cantilever beams AD and BF of equal flexural rigidity EI, which is equal to 24 multiplied by 10 raised to the power 12 Newton mm square, are connected by a taut steel rod DC. Have a look at this diagram here. You can see this is the fixed support here, right? And there are two cantilever beams. This is AD and this is BE. Both of these cantilever beams are having equal flexural rigidity EI. Okay, the value is given to you in Newton mm square. And they are connected by a taut steel rod DC, by a tight steel rod here, which will be in tension, a taut steel rod. Okay, and steel rod is here DC. You can see that this free end of upper cantilever beam is connected to the midpoint of the lower cantilever beam through this steel rod, which is having an elastic modulus of 200 gigapascal. And the question is now asking you, find the deflection of point D in mm. In mm you have to find out. Okay. If you look at the diagram has also given you certain things. The details of steel rod are given to you in the diagram. It is 5 meters long. Its cross-sectional area is also given in meter square, 3 multiplied by 10 raised to the power minus 4. As you can see that there is an external load P acting at free end E of BE, which is of 50 kilonewton. And now what question is asking you? It is asking you the deflection of this point D. How much this point will deflect by in mm. This is the question here. I would want that you just pause the video at this point of time and try to solve it on your own. Even if you are not able to reach up to the final step, go ahead. What I always say to you, that always try the question. Even if you do a mistake, it will become a learning for you. Every mistake will teach you something, right? So go ahead, try to solve the question. And now meanwhile, I am solving the question, and at every point in the solution, I would want you that you just pause the video. You got slightly better idea of the question, just pause the video and then try to solve. This is the approach that you have to use throughout the video course, not only in this example or any specific example. Throughout the examples that we will solve, the examples are going to be conceptual. I am not going to give you a formula based question that put the value, get the answer, or single statement examples. Those are not the type of examples that we solve in video course. The examples will be conceptual. They will be having combination of 2-3 different concepts. So it is possible that in the beginning you may not be able to start the question, but try. Even after that, if you have not started at that point, when I will start explaining the question, if you think that in next 1 minute, 2 minutes, you got a slight idea by hearing what I am telling you, at that moment again pause the video and try to solve it. Whenever you are solving question, always have this curiosity, right? This eagerness to try to solve on your own. This eagerness will really help you in long run in trying to solve the question. Your fear of solving the question will go away, right? It's very important. So at this point of time, if you can figure out the way to solve the question, go ahead. Even if you can't figure out, just try, just use the pen on paper. You will get stuck somewhere, don't worry. You can continue the video after that, and then after some point, if you get the idea, start again. Now, many of you will be starting the video course with mechanics or strength of materials, right? Like these subjects. So you have not seen me solving examples in further subjects, right? But once you will do that, you will realize that I just don't solve the question directly. Rather, I give you a 360-degree analysis of the question. Before starting the question also, I will give you many analysis points which you can learn and will help you conceptually. I will discuss the possible mistakes in the question, and I will also discuss some of the tips while solving the question. Let us start with the pre-analysis of the question. We have not started doing the question yet. Solving the question is not a matter of more than 2 to 3 minutes. I can quickly do that, but that won't benefit you, right? That will benefit you only when I am going to explain it in all the aspects. Every aspect I will explain. So have a look at this case here. Question has given us two cantilever beams, right? It has clearly mentioned AD and BE as two cantilever beams, right? And we have seen such cases of cantilever beams where a cantilever beam is present and a load is acting at the free end. You have to find out the deflection of the free end. That's a direct formula based answer, right? Similarly, you can have a case where load is acting at the free end, but you have to find out the deflection at the center. That is also a one-step question, right? You can solve this quickly. In this case, what question has done, it has linked both the cases, right? You can see here, it's a cantilever part, and at the free end, a steel rod is connected, which is connected to the midpoint of the other rod. And ultimately, the steel rod is going to transfer the force to the top cantilever beam, because a force is applied here, P. A force P applied here will try to move C in the downward direction. Steel rod might get elongated, we will see that, and that will pull the D point down, that will deflect the D. That deflection you have to find out, right or not? So the steel rod here, which is linking such simple cases together, is going to play an important role. You can definitely tell that, because steel rod's length is given, steel rod's area is given, even you can see the Young's modulus of steel rod is given, right? So if you look at the majority data which is given to you, most of the data you have been given about the steel rod, right? About these cantilever beams, it has directly given you the rigidity, but for steel rod, it has specifically mentioned the area, the Young's modulus, the length, right or not? So steel rod is going to play an important role, that is for sure. Now, how is it going to play the important role? We will understand that as we will keep covering the question. Now, at this point, you tell me, is it possible that the deflection of D will be zero, that it won't deflect at all? Is it possible? It is not possible in this case. Why? Because it's logical, no? Because force P is acting at this free end. This force P, this load P will try to push that point down. This beam will get slightly deflected, right? Like this, it has a certain flexural rigidity, which is a finite value, which means it will get slightly bent like this. This point C will move down. Obviously, if this point C is moving down, the steel rod will be under tension. It will be pulled down. And when the steel rod is pulled down, this point D will also be pulled down, right? It makes sense that this point will deflect. Its deflection will not be a zero value. That's correct. But tell me, can I relate the deflection of C with the deflection of D directly? Can I say that deflection of C will be equal to deflection of D? Or maybe deflection of C is more than deflection of D? Or maybe deflection of C is less than deflection of D? Can I say any of these things, or maybe option D, that we cannot relate them? It's a question in itself, right? Option A, option B, option C. And option D is data is insufficient, we cannot relate them. This is the question in front of you. Tell me, it does not require you to solve anything at this point of time. This length is also not required, area is also not required. Pause the video and think about it. Which of these three relations will be correct? Can we conclude something? Or maybe option D, that we cannot conclude. We can conclude actually. Both of the deflections will not be equal. Let me tell you which exact relation will be true here. In this case, the steel rod is getting pulled down because due to load P, C is moving down, so steel rod will be pulled down. Steel rod is getting pulled, it is under tension, which is very much obvious also because it is a taut steel rod, it's a tensed steel rod, right? And here also, even if you ignore that word, here also it makes sense that C will be pulled down. C is moving down due to load P. So the steel rod will be pulled down, right or not? So that pulling down of steel rod will tense it, right? You are pulling the steel rod. U means the point C, which is moving down, is pulling the steel rod below, which will tense it. Now think about the basics of deformation. If I have a certain rod here, suppose this is the same rod that we have, D and C. For this rod to transmit a force, if I want that a force F should act on this CD, what will happen? It will elongate, na? If a force F is acting in CD, it will definitely elongate. It is not rigid. Elongation means what? Elongation means the C and D. If I specifically talk about the tension, tensile elongation, which means C and D should move away from each other. It means they are getting tensed. It is tensile load, right? If the distance does not change, then it is no load at all. Or maybe the material is totally rigid, which is not the case here, right? Neither of the cases are present. Force is acting, definitely. If force is not acting, how will D get deflected? Force has to act. It means both of the distance between C and D will change because it is not rigid. And since that force is going to be a tensile force, we can say for sure that the distance between C and D will increase, right or not? And that can help you to relate the deflection of C with the deflection of D. How? Can you answer it now? If DC distance has to increase because DC is getting elongated, the bottom point should move more as compared to the top point. If C has moved by 1 centimeter by 1 mm and D has moved by 2 mm, basically the distance CD has reduced. So how is it possible that it will be in tension? And tension is necessary because it is moving down, na? It will get tensed. So the point C should move more with respect to point D, only then it will get tensed. Otherwise, it will not get tensed. If C is moving less, D is moving more, it is slacking it. It is not having a tensile effect, it is having a compressive effect, which is not feasible here because it is moving down, it will be tensed. So I can very clearly say that since deflection of D is occurring, it is non-zero, it has to move down, which is possible if a force is acting in the downward direction like this, which is possible when C is moving down, which ultimately means that it has to be a tensile force, only then this can transmit. And if you forget the concept now, just apply common sense. If force P is acting here, obviously this will be get pulled below, right? If somebody sits here, if I apply a force here, this will get tensed. It's basic common sense that you can say. Even without applying the concept, if you ask any 10th class student, he can give you a right answer. Good chances that he can give you the right answer only by intuition, right? So you apply the concept or you use the intuition, you will realize that CD has to be tensile, for which the distance between C and D should increase, which is possible when C will move more and D will move less. Only then it is possible, which means that the deflection of C will be more than the deflection of D. So this itself, you can call it to be a 2 mark or 1 mark gate question. And we have not even started the question yet. I have not told you any steps in solving the question yet. Right till the point of discussion, I can make 3 different questions that are very much feasible to be asked in gate. So this is the learning so far. We can clearly say that the deflection at point C and at point D are different. Now let us see how we will use this information to actually answer the question. Now moving ahead in this question, I have shown you 3 different free body diagrams. Incomplete, they are incomplete right now. This bottom one is representing BE, this top one is representing AD, and this point here is representing DC, right? Obviously this point in reality are connected, this point are connected. I am individually showing their free body diagram, okay? It is very much obvious that since C is moving down, so steel rod will be under tension. So this and this force is actually showing the tension force. You can see DC is under tension. And recall the concept that we discussed in the initial units, right? When we were covering the unit of axial deformation, what did I told you there? That if a body is getting pulled it will pull the other body also. It will help you in figuring out the direction of load, direction of force. So this is getting pulled. It is connected to point C. C will also get pulled. So this will be the direction, upward direction of C. Similarly, if you look at D, it will be having a downward direction, right? Basics of starting units, starting 2 units, that's what we discussed. So this is the free body diagram of the top AD cantilever. This is the free body diagram of specifically the steel rod, and this is the free body diagram of the bottom cantilever beam. Is it all right? Now at this point, as you can see, I have written possible mistakes. Some of the students can do mistake in making this. It's a silly mistake, it should not happen. But one possible mistake in this question is that when students are starting to solve this question, they will start from here, right? This is the most logical place to start from because we have been given the external load acting at that point. So we know this value of P, 50 kilonewton. So it makes sense to start from here. What students will do that they won't draw the complete free body diagram. As you can see, what I said that I have drawn free body diagram here, but in reality I have not drawn the free body diagrams. Support is not removed yet from there also, and from here also support is not yet removed. So it is not a free body diagram as such, and in hurry students can do this mistake that they will ignore the support, and what they will conclude from this diagram, they will directly take the moment about this point, and from this beam they can find out the expression between F and P directly, right? You take the moment, F multiplied by 2 is equal to P multiplied by 4. That will give you F is equal to 2 times of P, which is an incorrect expression. That's not how you can relate F and P. Why? They are in equilibrium. You can obviously take the moment about this point, but you have not removed the support yet. And it is possible that in such questions where your mind is towards different things, you may skip that. And that is very much important. Let me tell you why. I know you may think it's such a small point. It's very important here because this is not a statically determinate beam. It's a statically indeterminate beam. How can I say that? Let us have a look at the free body diagram. If I draw the free body diagram of this specific part here, I will be having, as we know that in case of free body diagram, when we remove the fixed end, we get 2 different forces and a moment, right? Horizontal force anyway is not going to exist here because there is no horizontal force on the loading side. So you will be having a moment and a load and a shear force as shown. In this case, how many values are unknown? Let's say this is R, this is M. R is unknown, M is unknown, F is also unknown, only P is known to you. So total 3 unknowns you have. And how many equations you can write? In this case, 2. Why 2? Horizontal one I have not shown. Na? If I show horizontal one also, then there are 4 unknowns. Now, how many equations can you write? 3. Fx, summation Fx0, summation Fy0, net moment 0. How will you find out these 4 values? By those 3 equations, you cannot find out. So using the statics condition, you cannot solve it. It's statically indeterminate beam. Even if you look at the entire structure also, that is also statically indeterminate. Because these supports here also will be generating same thing, moment and the load. But externally, if you look at it, only P is given to you, right? So if you write the equation, the 3 equations there, it won't be sufficient to find out the 2 unknown reactions or 3 unknown reactions here also and here also. So this complete thing is statically indeterminate, and that is a possible silly mistake. Whenever you get a question, firstly try to determine whether it is statically determinate or indeterminate. And how you can do that, let me quickly tell you how you can train your mind to do that. Generally, if you have a beam which is not connected to a different members, it's a regular beam like we have seen, there are chances that it will be statically determinate. But how things become statically indeterminate, what I have taught you? When there are additional redundant connections, then there are chances of the beam or any such component becoming statically indeterminate. Here this DC is an additional connection here. If DC was not there, then only 3 unknowns were there, right? 3 equations, 3 unknowns. You could have solved it. But it is an additional connection which as such is not required for the stability of the cantilever beam, right? Cantilever beam can exist even without DC, right? But it's an additional connection, means additional unknown values. Such cases can be statically indeterminate. So whenever you get a question where you can see that there are some additional connections, maybe in the form of rod, maybe in the form of some load, you can see the question and figure out what are the connections, different connections. We have discussed about connections in strength of materials, also in brief when I was telling you about loads, and in mechanics also we have covered different types of connections. So that will help you in just having a hint that maybe it's statically indeterminate, and you can quickly check it by making the free body diagram. You can quickly check it, like here quickly we have checked it. So this is a statically indeterminate problem, and in this situation we have to now write the equations of deflection also. The compatibility equation also we have to write, so that we can get one more additional equation. Now we need one more additional equation because this is an additional unknown. You need an equation, right, through which you can find out, you can relate the force. Now let us see how we can get that equation, that additional deflection equation, how we can get. Let us see. So as you can see here, this top beam is going to get deflected, let us say by del 1, and this bottom beam is getting deflected, but the point C will get deflected, let's say by del 2. P load is acting at point E. As I told you initially, what I told you when I was telling you about the deflection of del 1 and del 2, or del C or del D, that both these values are different, and clearly del C is more than del D, or del 2 here is more than del 1. Only then it can be, this rod can be under tension, right? And if you just think one step ahead, you will figure out that deflection of 2 minus deflection of 1 is equal to deformation of rod CD, right? If C is moving suppose by 2 centimeter below, D is moving by 1 centimeter below. So effective elongation is 1, 2 minus 1. This moved down by 2. But if D was at its own place, then net deflection will be 2. But D is not at its own place. D will also move in the same direction. So movement of D will reduce the deformation, will reduce the deflection, because deflection or deformation of CD is the increase of distance between C and D. So if C moved by 2, increase is of 2 centimeter. But D is also moving down. Na? If D moved down, the distance will decrease by whatever will be the value of deflection at D. So deflection of C, which is del 2, minus deflection of D, which is del 1, will tell you effective change of length of CD, tensile elongation, how much is the tensile elongation, which is del rod here. This is an additional equation which we have got, which will actually relate both of them also, and which will give you, as I told you, one more additional equation required for the compatibility. So what can we call this equation? This is a deflection, this is a deflection compatibility equation, right? Now what do we need to do? We need to find out the value of del 2 and del 1. The del of rod is slightly easier to write the expression at least, right? For del of rod, what do we know? Del is equal to PL by EA. P means the force which is acting there. F is the force which is acting. In this case, I showed you na, in the free body diagram, F is the force acting here. So here, its deflection will be the force acting multiplied by its length is H, suppose, and E and A. E value is given to us in the question. For the steel rod, A is given to us, H is known to you, F is clearly an unknown value. We want to find out the value of F, right? So deflection of this rod, its expression is very much straightforward. No point, no difficulty in that. So this you can write in terms of force F, right? Look at del 1 here. Del 1 also you can write in terms of F. How? Look at the free body diagram here. If I show you the free body diagram, this force F is going to act here also, right? This F will be transmitted throughout. So this will be acting at point D also, and which clearly means that the deflection of D will be equal to FL cube divided by 3EI, right? Force acting at the free end of a cantilever beam. Direct expression we know. L is the length. This is L, this is L, this is L. L is equal to 2. We know that. EI value is given to us in the question. If you look, EI value is given to us for AD also and for BE also. So EI is known, length is known, 2 meter is the length, F is unknown. So deflection of D is also known in terms of F, which is deflection. It's not del D, it is del 2 or del 1. So in the diagram, this is del 1 here, deflection of D, which is F L cube divided by 3 EI, right? So del 1 is also known, this term is known in terms of F. This is also known in terms of F. What about del 2? Let us see. How we can find out the deflection of 2? It's not difficult. It's something that you can use any of the method of slope and deflection to find that out. But I would prefer that if you directly find that out using the superposition rule that I have told you. In single step, you will be able to get it without using any of the slightly lengthy methods. Try to do that in the meantime. So this particular deflection diagram clearly tells you del 1 is equal to FL cube by 3 EI. This is the diagram for the bottom cantilever beam. And in this case, you need to find out the expression for del 2. What can you do for that? As I told you, different methods you can follow. I would prefer superposition rule to find out the answer quickly. Shift this load P at the point C. What will happen? You will have a force in the downward direction, force in the upward direction. These two are going to form a clockwise moment. So that is what I have shown here, right? And since here P will be acting in the downward direction and F is acting in the upward direction, so I can replace them by a single force which is in the downward direction, P minus F, because here F is acting in the upward direction. No? F is acting in the upward direction. If I shift the P here at point C, how do I shift it? Like this and like this. These two are going to form a moment, clockwise moment. This force is in the downward direction P and this F is upward, acting at the same point. Let's make things easier. Let's replace them by a single force, P minus F in the downward direction. If I write F minus P, I have to write it in the upward direction because F is going up, which will be reduced by a P amount because P is down. Then I have to show the direction up. Ultimately, if I am saying F minus P is the expression, means F but slightly reduced by P, right? But when I write P minus F, what I am saying that it is acting in the downward direction because P was acting in the downward direction, but amount has been slightly reduced by F. Why by F? Because F was acting up, right? So this is important to note here. So in the downward direction, P minus F is the load acting. The moment acting due to this couple will be P multiplied by this distance, which is L here. So moment is of P, L, right? This thing when you start doing, when you start practicing, you will be able to do like this, right? Right now, if you are starting, if you have not solved enough question, you may think that, sir, it is slightly tricky to do. But once you start practicing question, doing this is a mental calculation. You don't even require to use pen and all for this. You can directly imagine in that yes, it will be F minus P. You can directly write it. It's not recommended to do. There are chances of silly mistake there. Try to properly write it. I am just giving you an example of it. Okay. So in this case, this is the deflection diagram that we have. And from here, we have to find out the deflection of this point here, right? We have a load P acting, we have a moment acting. It's very easy to do now, right? You can directly write the expression for this, and this is L, this is L. So for the load P minus F, this is the expression, net load P, what we call in the formula, here it is P minus F. So net load L cube divided by 3 EI. This is the deflection due to this load P minus F. And what about the moment? What about the moment? For the moment, it is ML square divided by 2 EI, right? M here is PL. So ML square divided by 2 EI. Now you just have to simplify it. This will be PL cube by 3 EI minus FL cube by 3 EI. PL cube by 3 EI plus PL cube. This will become PL cube, no? PL cube by 2 EI. If you add them, you will get 5 PL cube by 6 EI. Minus FL cube by 3 EI will stay there. So this, what you have got is the del 2's expression. As I told you, there are different ways we have discussed all the methods. You can choose any of them to get to this expression. Now comes the part where you have to put this value. Where? Here. Del 2 minus del 1 is equal to, the change in length of the rod, right? Del 1 we know in terms of F. Del of rod we can easily write in terms of F. Del 2 expression we have found out. And if you look at this expression, again EI is known, P is known to you, 5 kilonewton value acting is known, F is the only unknown. So this equation, what you have here, if you put all the values and solve, you will get the value of F from there. And once you have got the value of F, question is very easy now. Once you have got the value of F, let me show you how. The del 1 expression, del 2 expression I have put here. Now you have to simplify this, right? How do you simplify this? That's also one small point to note here. F and F are having, we are having in these two expressions, send it on the right hand side. So it will become this term is equal to this term plus this term, right? From there you take out F as common, and whatever will be left, send that to the denominator on this side, right? And then solve it. I have done that already. So if you do that, this is the expression that you will get by simplifying this expression here. Yes, and let me add one more point here in case you are still thinking. Del of rod is PL by EA, the very common expression of deflection that we know. The force acting is F, the height of rod, the length of rod I have written as H. This is the Young's modulus of steel, and area A is representing the area of the rod. Okay, so I just cleared the terminology here, and now you can just simplify it. Upon simplifying, you will get this expression. As I told you, send it on the right hand side, take F as common, right? So what you will be having, 2L cube by 3EI plus H by ESA. Send that on the denominator of left hand side. So you will get 5PL cube by 6EI divided by that term. Now put all the values. While putting the values, be careful about the units. You can see different units in this question. How? You can see that EI is given to you in Newton mm square, right? This is given to you in gigapascal, this is given in meter, this is given in kilonewton. So you can see a good variety of units. I have told this to you in the very initial unit that whenever you have such different collection of units in questions of strength of materials, go for the convention where convert all the forces to Newton and convert all the length units to mm, right? So which automatically means that wherever you have a unit of pressure or stress, convert that to megapascal, because megapascal is nothing but the units in terms of Newton and mm, right? Newton per mm square. So here it is already in Newton and mm, which is fine. Gigapascal is written, which you can convert to megapascal by multiplying it with 1000. This meter you convert to mm by multiplying with 1000. Meter square you convert to mm square. Kilonewton you convert to Newton. So ultimately the unit of forces will be converted to Newton, the units of length will be converted to mm, and if any direct value is given like gigapascal or pascal, convert that to megapascal, which is nothing but the unit of stress in terms of Newton and mm. And now you put the values. What answer will you get of the deflection will be in terms of mm. What answer will you get of Newton will be of force will be in terms of Newton, that you can convert. This is not the final answer that I have got. Newton you will get. If you solve all the values by putting in terms of Newton and mm, you will get the answer in Newton. Convert that to kilonewton. This is the value of force that you will get. And now it is very easy. You have found out the value of force. You need to find out the deflection of D, which is deflection of 1, del 1, which is nothing but FL cube by 3EI. F you have calculated, L, E, I, all values are known to you. Just put the value here. The kilonewton value I converted to Newton by multiplying with 1000. The length here, FL cube, is 2 meter. If you look at it, this is 2 meter. So 2000 mm I have written. 3 multiplied by EI was directly given in Newton mm square. So just put the value and solve. You will get the final deflection of D as 5.05 mm. One more point to note here. Those of you who would have tried solving it and would have used different approaches, would have done some silly mistake maybe, would have missed some concept, all of you will get an answer which is kind of a multiple of 5.05. Some of you who don't do some pre-analysis, you just start and do some silly mistakes. Some of you may get zero answer also using calculation. There is a way doing a specific mistake. If I discuss that, it will become too detailed, but there is a specific type of mistake that is possible in this, which can get you to an answer of 0. It is possible to get an answer which is double of this, 11.11 mm. That is also possible to reach. This is the right answer obviously, and one more variation you can consider. So options, if you get in this question, I will call that a difficult question. NET would be easier here as compared to MCQ, because in MCQ you get a wrong answer, you see the option, you will tick it, you will say I have done correctly, my answer is written in at least one of the option, you won't reconsider at your solution, right? So this is the question that in front of you. You can see that it is a question which may not be asked directly in GIT. It is slightly more detailed than what GIT asks, but a subset of this question can definitely be asked. As I told you in the very beginning, how do you relate the deflection at C and D? It's a very feasible question that can be asked. Let us move to the next example now.